The other kind of mass is gravitational mass. Now this is completely different than the mass needed to change the direction of a particle, to change its momentum. In fact, this kind of mass is roughly gravitational charge. So we can write a force in general as some constant times charge 1 times charge 2 over the distance between them squared, in the direction between the two particles. So in this case, if I have particle A here and particle B here, this would be the distance between them, and then of course this is the r hat direction. Okay, and so this is just any kind of force that has some kinds of charges involved. So in the case of gravity, this constant is just called g. It's the gravitational constant. Mass 1 and mass 2 act like the charges over r squared in the r hat direction. So again, we see that this is the same force that we have between charges in electromagnetism when we're talking about the force of electricity and the force of magnetism. This is the same thing now, but now the charge is replaced by mass. So again, this has nothing to do with changing the momentum. It has to do with measuring the attraction between two objects. One other difference between the force of gravity and the force of electromagnetism, of course, is that gravity never repels. Like, gravity always pulls objects together. But let's look at the case where we say that m2 is the mass of a planet. Okay? Now we can write force is m1 times this g vector, where g is minus big G, the mass of the planet, divided by the radius of the planet squared in the r hat direction. In other words, we're saying that, let's say we have a planet like Earth, and we're up here on top of it performing some experiment. Okay? So the distance of this ball, if I'm going to drop a ball, the distance of the ball above Earth's surface is much smaller than the radius of the Earth. So the gravitational force is basically just proportional to the radius of the Earth square. So this force now that we have, that's a mass times this vector, this acceleration vector, this is what we call weight. So if I say something like I have a weight of so and so pounds, in the metric system, a pound is proportional to a newton, right? It's the same type of unit, and this g, the magnitude of g, is about 9.8 meters. I'm sorry, 9.8 newtons per kilogram, which is a meter per second squared. But this is just on Earth, right? So in this case I'm writing g on Earth, but on every planet, on every object, this g would be different. But whenever we're talking about experiments going on Earth, like our weight on Earth, it's the mass times this g on Earth. So that wraps up this chapter. In the next chapter, we're going to start talking about things that are a little bit more fun and a little bit more kind of physicsy. We're going to start talking about systems of particles. We're going to start talking a lot more about how a big group of things interacts. So we're going to start looking at more realistic scenarios than just kind of like one particle interacting with another.